Drive through a highway tunnel and you are inside a sealed concrete tube, sometimes several kilometers long, with hundreds of other vehicles. All these vehicles are burning fuel and producing exhaust. The air you are breathing contains carbon monoxide, nitrogen oxides, and other combustion byproducts. These pollutants accumulate in a confined space with no natural ventilation. And yet, in a properly operating tunnel, the air quality remains within safe limits. Drivers do not experience symptoms of carbon monoxide poisoning. Visibility is maintained. Even in a fire, the ventilation system manages smoke for safe evacuation. None of this happens by accident. Highway tunnel ventilation is a precisely engineered system designed around specific contaminant limits, traffic flow, and emergency conditions. The engineering decisions that make it work are far more complex than simply blowing air through a tube. The primary contaminant of concern is carbon monoxide. Vehicle engines produce CO as a byproduct of incomplete combustion. CO is toxic at concentrations reached relatively quickly in a confined space with heavy traffic. The World Health Organization guideline for CO exposure over a 15-minute period is 100 parts per million. In long tunnels, CO could exceed this in minutes. The ventilation system must maintain CO below the design threshold continuously at every point along the tunnel length, including the worst-case locations. Nitrogen dioxide is the second critical contaminant, particularly for diesel traffic. NO2 is more toxic than CO and causes a characteristic yellow-brown haze. Modern tunnel ventilation uses visibility as a direct control parameter, with optical sensors measuring the tunnel air and triggering increased ventilation when visibility drops. The simplest approach, longitudinal ventilation, uses the piston effect of traffic. Moving vehicles act as pistons, dragging air in the direction of travel. In a unidirectional tunnel with sufficient traffic, this piston effect alone can maintain air quality. But the piston effect is inherently unreliable. It depends on speed and density, reverses if direction changes, and fails completely when traffic stops in a congestion event. Relying on it as the primary strategy is only acceptable for short tunnels with unidirectional traffic and low congestion probability. For tunnels longer than approximately 400 meters, or any tunnel with bidirectional traffic or significant congestion risk, mechanical ventilation is required. The dominant system used in modern road tunnels is jet fan ventilation, a longitudinal system in which axial fans are mounted in the tunnel ceiling. These fans generate a longitudinal airflow along the tunnel by accelerating the air mass in the desired direction. Jet fans do not move air through ducts. They operate in the open tunnel cross-section, creating a thrust force. This force is transmitted to the tunnel air through momentum exchange, building up a bulk airflow along the tunnel length. A jet fan installation for a typical two-lane tunnel might consist of 20 to 40 individual fan units. Each unit produces a thrust of 1,000 to 2,000 newtons, spaced at intervals of 80 to 120 meters along the ceiling. Each fan is reversible. It can thrust in either direction, allowing the system to push air toward either portal depending on traffic. The fans operate at variable speeds, controlled by a central management system that monitors contaminant concentrations and visibility. It adjusts fan output to maintain air quality within specified limits while minimizing energy consumption. The control logic is complex. Air quality varies. Concentrations are highest where traffic density is greatest and natural dilution is weakest. Running all fans at the same speed pushes the contaminated air mass toward one portal, potentially creating high concentrations near the exit. The system must manage the spatial distribution by adjusting individual fan speeds to minimize peak concentrations throughout the tunnel. Portal effects, natural airflow caused by wind at the tunnel entrances, complicate this management further. Wind blowing into one portal creates a natural longitudinal airflow that may assist or oppose the mechanical system. A strong headwind at the entry portal can overwhelm the system and push contaminated air back into the tunnel rather than exhausting it. Meteorological monitoring at the portals is integrated into the control system, and fan operation is adjusted in real time. For very long tunnels, those exceeding approximately 3 kilometers, longitudinal ventilation alone becomes insufficient. The contaminant load exceeds what portal exhaust can handle without generating unacceptably high concentrations in the middle sections. These tunnels require transverse or semi-transverse ventilation, systems with dedicated supply and exhaust ducts running the full length. This introduces fresh air and extracts contaminated air at distributed points rather than relying on longitudinal flow to reach the portals. A fully transverse system has both supply and exhaust ducts, introducing fresh air through floor-level grills and extracting contaminated air through ceiling-level dampers. The supply and exhaust flows are balanced to maintain a slight positive pressure in the tunnel, preventing the infiltration of contaminated air from adjacent spaces. This approach provides precise control of air quality, but requires more infrastructure. Ducts must be built into the tunnel cross-section, adding construction cost and complexity. The semi-transverse system uses only one duct, either supply or exhaust, combined with longitudinal flow to handle the other function. Supply semi-transverse systems introduce fresh air at distributed points and rely on longitudinal flow to carry it and mixed contaminants to the portals. Exhaust semi-transverse systems extract contaminated air at distributed ceiling points, while fresh air enters through the portals by longitudinal flow. The choice between these approaches depends on the tunnel geometry, traffic characteristics, and emergency ventilation requirements. Emergency ventilation, the response to a fire, is the most demanding design scenario and often drives the entire system design. A fire produces smoke that is life-threatening to occupants. The objective is to maintain tenable conditions in evacuation routes long enough for occupants to reach safety. Smoke rises due to buoyancy and stratifies. The hot, buoyant smoke layer rises to the ceiling while cooler, cleaner air remains at a lower level. If this stratification is preserved, occupants can move below the smoke layer toward the exits. This is critical for survival in the first few minutes. If stratification is disrupted by strong longitudinal airflow or improper mixing, the entire tunnel atmosphere becomes untenable rapidly. Emergency design must balance competing requirements. Longitudinal airflow must prevent backlayering, which is the upstream spread of smoke against traffic flow. But airflow must not be so high that it disrupts smoke stratification and fills the evacuation paths with smoke. The critical velocity is the minimum longitudinal airflow needed to prevent backlayering for a given fire size and tunnel geometry. For bidirectional traffic, emergency ventilation is more complex because there is no defined upstream direction. Smoke can spread in both directions from the fire. Some tunnels use point extraction systems, ceiling exhaust dampers near the fire that extract smoke before it can spread, combined with directed longitudinal flows. The control system must identify the fire location from detector inputs and open the appropriate dampers within the specified response time. Detection systems include linear heat detection cables along the ceiling and CCTV with automatic image processing to detect smoke signatures. The response time from ignition to full emergency mode is a critical safety parameter. Every second of delay allows smoke to spread further. The power supply for tunnel ventilation must be reliable under the same emergency conditions that require it most. Normal grid power is supplemented by emergency generator systems that start automatically on power failure and can supply the ventilation fans and emergency lighting within seconds. The ventilation fans are designed to operate in high-temperature smoke-laden air for a defined period, typically 120 minutes at 250 degrees Celsius, to ensure they remain functional throughout the evacuation and firefighting phase. So why don't highway tunnels run out of oxygen? Because the ventilation system is not simply moving air through a tube. It is managing a continuous, spatially distributed contaminant load, responding dynamically to traffic flow, portal winds, and air quality sensor inputs. And it is designed from the outset for the emergency condition, the tunnel fire, where the same fans must switch to smoke control in seconds and must maintain tenable evacuation conditions long enough for every occupant to escape. The tunnel you drive through in 2 minutes was designed around a fire scenario that could last 2 hours. Every fan, every sensor, every control algorithm reflects that design basis. The air you breathe inside is safe not because the tunnel is open, but because an engineering system ensures it stays that way. If you've ever wondered what happens when the ventilation system itself fails, how passive design features provide a last line of defense, that scenario and the engineering margins built into tunnel design is something I've covered in another video.